Welcome to the Conservation of Energy Lab. Our first exercise is what I call the loopy-loop lab. We're going to take a ball, roll it down the track, and we're going to see what gravitational potential energy is going to be required for it to go entirely around the loop. So the first exercise is just measuring the loop, the diameter of the loop, and that's the radius, and figuring out what height to release it from so that the ball barely makes it through the loop. Now, in the theory section, we talk about what happens at the very top of the loop when the ball is just barely holding on. The gravitational weight of the ball is what provides a centripetal force at that point. Remember, centripetal force is center-seeking force. It always points towards the center. We talked about that when we mentioned Newton's laws. So I'm just going to give it a whirl and see if it got pretty high up. Oh, actually, it was pretty close to the actual value. Now, what we're going to do is I'm going to put it up. If I do it a little bit too low, like this, it falls off. But if I go really far up, it goes no problem. Now, ideally, it needs to be the same height as the height, then the gravitational potential energy will change completely into kinetic energy. But there's other energies that are present in this exercise. It's not only linear kinetic energy, but rotational kinetic energy. And the largest thing that's going against us are the frictional forces. So even though the ball is rolling, there's still friction and it's eating away some of the energy. So I have to move the ball up quite high, much higher than what you'd predict theoretically without friction. So we're going to do the calculations assuming there's no friction. And there's also another energy present. If you use one of the other senses, the sense of hearing, you hear the ball rolling. So some of the mechanical motion is changing not only into heat through friction, but also into sound energy. So that actually means we have to release the ball from a higher point than we normally would. So let's just try a couple things, and then we're going to, all right, so that's a little too high. I'm going to move it down a wee bit. All right, so it's sort of losing contact, but it's still, I'm going to move it down a little bit. All right, sort of right around that area right here. A little bit higher than this. I know you probably can't see it, but okay. So I'm going to mark that point, and we're going to go measure the height of that point, because in my estimation, that's the point at which the ball barely makes it. So now let's measure the diameter. There's a loop. So let's just, I've got this tape measure here. I'm going to put it at the top, and we're going to measure the diameter of the loop, so at the bottom. So it looks like it's almost exactly 30 centimeters. Now that's the diameter, so what would the radius be? The radius is obviously half of 30. Okay, so let's now briefly go over here so we can measure the height that I release it from. Oops, wrong way. I'm doing it upside down so you guys can see it on here. But can't see the bottom of my tape measure. Closer. There we go. All right, so I've got it sitting up there, and it looks like it's around 58. I gotta make it nice and taut. 57.4. So 57.4 would be my initial height. And what we're going to do now is go on to the second exercise in which we're going to calculate the critical velocity. That's the velocity when the ball just barely is making it around the track. It's a speed at which the only force acting in the ball when it's at the top of the track right here is gravity.